Hello and welcome back to Learn It from a Layman. I am Carl Christensen, joined by Tim, the substitute chemistry teacher, Cox.
And is much more credit than I deserve.
Haven't you seen Hook, Tim? When we've had discussions about Hook,
Yeah.
the scene where the insult scene with Rufio.
Oh.
His
You
first
substitute chemistry.
he says substitute chemistry teacher. Yes.
It's all the negatives of a chemistry teacher with none of the competency.
Yes, I've got two anecdotal pieces of experience with chemistry teachers, but that'll come sometime during the podcast. Today, we're talking about the basics of chemistry. At least hypothetically, we are. Tim, I thought of all the various guests we could have on to talk about chemistry, all the knowledge we could bring to bear. And I thought, what would be the best is Tim.
And then he woke up and said, "What have I done?" So
the message was already sent. Nightmare. Anyway, no, Tim will do a good job, I think. And if he doesn't, I'll dock it from his pay.
Refunds for everyone. Yes.
That's right. So, you can ask for your money back for this podcast. Okay. All right. Let's talk a little bit about chemistry here, Tim. As I was telling my daughters today that I was doing a podcast on chemistry, they said, "What is chemistry?" How would you answer that question, Tim?
Okay. Well, I would answer by saying, and I'm just going to start by noting that my research for this was done almost exclusively with Crash Course Chemistry, which is a great like YouTube series. There's a crash course stuff on different topics, history, and all sorts of topics, and they do a great job. So if you want to really learn and understand from people who actually know what they're talking about, I recommend you to Crash Course. Hank Green and John Green, they do a great job. Anyways, so
all right, so 2 minutes and 30 seconds into the podcast, you have asked our listeners to leave.
Yeah, please close this podcast now. And just that little X right there. Yes, that's the one. And okay. But
okay, yeah, chemistry.
Due to the vagaries of fortune, you're stuck here with us. So here we go. Chemistry is an understanding of how our world works together and how the components of everything around us interact to form and make everything as it is. I don't know. Does that probably work? Okay. I'll keep going
here. It sounds like a middle school teacher trying to get buy-in from their students,
Yes.
Like overselling the subject so that it sounds interesting.
Yes, that's right. This is all cool. Now, so the chemistry, what it does, at least to understand it properly, we need to understand that everything is made out of fundamental building blocks. And so you have yellow bile, black bile, blood, and phlegm. These are the four humors. And from wait, shoot. Sorry, I'm looking at the wrong page.
Look at a variety of chemistry here that nobody's learned since the Dark Ages.
That's right. No, and it is interesting actually to look at the history of chemistry. And sorry, but since history is my jam, I'm going to take that route. So chemistry has been attempted for millennia as people have tried to explain how the world works. So the four humors theory that I just suggested, that goes back thousands of years, and people would observe different fluids and say, well, things must be made out of these fluids interacting or whatever. Later on in the Middle Ages, you had alchemy, which anyways, alchemy, you had
also known as the good old days.
The good old days, just the good old boys. Sorry, I just went to Waylon Jennings. That's but it's never wrong to go to Waylon Jennings. So
It's also,
alchemy was in the, I was saying this very broadly, in the Middle Ages, people believed that you could, they saw that things happened with different substances that would interact, and they believed that you could make um, good things happen. And by good things, principally, we're talking about turning things into gold. And so there was these, all of these tinkerers, experimenters would try to turn things into gold. And in fact, the word alchemy, I looked it up. It's actually a compound. You have the Arabic word al, the, and then coming from the Greek word chemia, which means the art of alloying metals, or possibly something poured out or flowing out, like liquid or gold. Anyways, so this is where our word chemistry actually comes from. A chemist would have been someone who engaged in alchemy, um, but we had to stumble through a lot of poorly constructed false theories about how things worked, and erroneous notions like, yeah, we can mix stuff together and turn it into gold, which is, of course, pure garbage. There were other false theories like there's this concept called phlogiston, or this idea that, to explain how compounds changed after chemical reactions, well, there must be this unknown substance called phlogiston in there, and when we burn this substance, the phlogiston gets removed and it leaves a different substance, which is, of course, also garbage. But that's all they could figure out. But over time, as people started putting observations together, we started to figure out more and more of what was actually going on. And we started to learn things like, for example, there's this guy called Lavoisier. Sorry, my Francophiles. He was killed in the French Revolution, but before he was killed, he started to
because who
kind of,
wasn't?
the what?
I said because who wasn't?
Yeah, who? That's right. It was all the rage at the time, and I mean rage in the literal sense. But
Yes.
anyways,
Okay, sorry.
He started to put together all this research and kind of move us past all of these kind of bunk theories, and they started to observe things like, well, hang on, when something is burned in the open air, it becomes lighter, but when you burn it in a sealed container, the mass stays the same. So they started to make these realizations that over time turned into these laws, like the law of conservation of mass, which is, and I'm reading here, matter can neither be created nor destroyed, though it can be rearranged. Mass remains constant in ordinary chemical change. Um, and so, anyways, and one of the fundamental breakthroughs was the discovery of what came to be known as Brownian motion. This botanist observed that the pollen, he was looking at pollen particles under a microscope, and he saw that even though there was nothing acting on them, they just jiggled and bounced around. And he's like, what's going on? Um, and he knew that something was happening, and it was actually Einstein in 1905 who who mathematically demonstrated that we could explain Brownian movement, this random jiggling movement of particles, or of these bits of pollen, by assuming that there were microscopic particles flying around and bumping into the pollen. And as they bumped into it, they would make it jiggle and make it move. And so from that was kind of the establishment of the atomic theory of chemistry, which is how we understand the world of chemistry today. And it has been very productive. Um, Keeping in mind we're talking about theory as in a set of observations, disparate observations, demonstrated through experiment, not like theory is in this is just someone's whim or guess. So anyways, so atoms are the thing, and that's where we're going to start today, though I suppose it's erroneous to say that we're starting at this point in the podcast. But so we're going to talk about atoms. We're going to talk about the periodic table of elements, and then we're going to talk about crazy chemical stuff. That was
crazy chemical stuff. You can quote us on that.
Yes, that's right. That will be on our merch. You can buy a T-shirt that says "Crazy Chemical Stuff." Learn it from a layman. It's going to be great.
Crazy
Okay.
and less crazy. The actual day-to-day interactions of the layman that where chemistry actually comes to bear. So both.
I'll notice that this is the second time you've used "to bear" the phrase, and every time you make me think of like a big grizzly bear, and which kind of makes it sound interesting. You know, like when you said the knowledge we can bring to bear, and you know,
I said that.
Yeah, or when you were like, we could have gotten an expert, but we got Tim because we.
Oh, okay.
But I'll just
All right.
say, if we're bringing knowledge to a bear, I don't want to be the one carrying the plate.
Well, I I would be so lucky to have you bring anything to a bear, Tim.
Yeah, it would actually be a real trip. The, we can put that phrase
Okay.
on our merch too. Coffee mug.
Yes.
Coffee mug.
Okay. All right.
To bear.
Okay.
Back
so
to
atoms.
Okay, so you probably know the basics, but just to make sure, everything is made of atoms, including the air you breathe, the chair you're sitting on, and you. Atoms are composed of three fundamental particles. You have the proton, the neutron, and the electron. And you can think of atoms, probably the best way to visualize them, as far as I understand, is you've got a mass, a clump in the middle of protons and neutrons, and then you have these much, much smaller electrons that orbit around each clump. Strangely, physically, it would probably be akin to a solar system. But of course, the interactions are very different. When we talk about atoms, we have to talk about charge. When we say charge, we're talking about positive or negative. And when we think of charge, you can think of a magnet. One end of a magnet is positive, the other end is negative. And the positive and negative charges attract each other. If you put a positive end of a magnet next to a negative end, they will stick together and attract each other. A negative on a negative, they will repel. So you have positively charged protons, positive, are in the nucleus. By the way, much more massive than electrons. I think the number is something like 1,800 times larger or more massive. And then you've got the negatively charged electrons that orbit around the proton. Neutrons have no charge. But they are still important. Without neutrons, an atom wouldn't be able to exist because all of the protons would not be able to pack it in together. They would repel each other. So the neutrons give us just enough, I guess, buffering to help the protons stick together. They are held together by the strongest force in nature, the strong nuclear force. But anyways, enough on that. Now, how many protons are in the atom is the most identifying piece of information about an atom. The number of protons determines what an atom is. In other words, what element it is. Is it carbon? Is it hydrogen? Is it boron? Change the number of atoms or of protons in the nucleus, and you've changed what that atom is. Incidentally, this is very hard to do and very rare. Like the only off the top of my head, which conceivably isn't very much, but I think this is probably good information.
Wait, was that a short joke?
Short, such a trap. Go take some knowledge to a bear. The only times I can think of where an atom the composition might be changed would be in a nuclear explosion or or reaction, or in the center of the sun, which I guess would be a nuclear reaction, by definition, a nuclear reaction. But basically, the only places where there's enough power to to change an atom would be in the intense pressure and heat inside a star, or in a nuclear reaction, like a nuclear bomb, or say the nuclear fission of like a nuclear power plant, where you're splitting atoms. And in all these cases, there's an incredible amount of energy involved. For most situations, including all these situations that you're going to see face to face, I hope, protons stay the same; they don't change.
Yeah, so that's sorry.
Oh, sorry.
Just to throw in real quick, I call back to our podcast on quantum physics. I think so. Peter, who we had on at the time, a cousin of ours as well.
He knows real stuff.
Do you say he knows real stuff?
Yeah.
We're talking about the forces of the fundamental forces, the weak force, the strong force. There were more than that. But the strong force is the one that binds together the nucleus, and it's called strong for a reason, which is what you're just talking about. Like, it's super hard to break a nucleus up. So,
or to pack more into a nucleus. Either way, yeah.
Right.
I think gravity would be one of the other fundamental forces, right?
And, that sounds right. I'm looking right now. You can continue.
And now I want to get them all. How many are there?
Electromagnetic force? I don't know.
Okay. Ooh, what if we did like we made T-shirts?
Gravity, like, strong, weak, and electromagnetism. We got them, Tim. We got them.
All right. Cool. Let's make a T-shirt, and like on the sleeves, like pointing at the biceps, it'll have an arrow saying "strong force." Huh? I think that's some good merch.
Nope. Okay. I think you were going somewhere with this before.
I was going somewhere real. Okay. Yes. So, where was I going? We were atoms, strong force,
atoms, nucleus, and you're talking about the. You were about to move to the electrons.
Yes. Okay. So, as far as chemistry goes, not much action in the proton. It's just sitting there. But the electrons, there's a lot more that goes on there. So electrons bring balance to an atom, right? They have the negative charge bouncing at the positive charge of the proton, but electrons can bounce around. They can get knocked off. An atom losing an electron doesn't change its what it is. It doesn't change its constitution to a different element. It just loses a charge. So it might be, if it loses an electron, now it's got a slightly positive charge. If it gains an electron, it might have a slightly negative charge. And please take this with a grain of salt and know that this is oversimplified knowledge from my AP chemistry class that I took more than a few years ago.
What, three then? A few is three.
At least three.
Saying 4 years ago, yeah.
If we presume that the maybe is a lie. So the some elements, based on their composition, might tend to be positive or might tend to be negative, and also, so what happens is everything wants to kind of achieve balance. That's what everything will tend to lean towards is the wrong phrase, but they'll tend to move towards being balanced. So a proton with a slightly positive charge, say it's missing an electron, and an atom with a slightly positive charge and an atom with a slightly negative charge, they both are kind of seeking that balance, that neutral. And so just like if you put two magnets in a box and shake them together, the positive and the negative will eventually join together. Well, same thing with two atoms that have maybe a slightly positive, slightly negative charge. If you put them together, they will kind of stick together. And what happens is those the well, let's just leave that. That's probably all I'm qualified to explain. But because one has a positive charge,
I mean,
one has a
some would
negative
argue
charge.
you weren't qualified. Sorry, some would say you weren't qualified to explain that either. So.
That's true. But as long as I keep on talking, those people will be harder to hear. So, anyways,
Okay.
And so what happens is atoms will tend to bind together. This is why you'll find, for example, an oxygen atom will often, you're not often going to see it just flowing around by itself. They'll often be bound together with two hydrogen atoms. And those hydrogen atoms will kind of stick onto the oxygen atom, and they'll kind of balance each other out, and you'll end up with a stable. And this is where, so if elements are pure atoms, so if I got a whole container full of pure oxygen, that's just the element of oxygen, or a whole thing full of pure mercury, that's just mercury. But when atoms join together, we call those molecules. And so, for example, two hydrogen atoms joining together with an oxygen atom, we have a molecule of dihydrogen monoxide, which is commonly referred to as water, of course. And so understanding how these molecules are made is a big part of chemistry. And there's a lot of math that's involved in kind of explaining, because you're working with numbers here. For example, the number of protons and the number of electrons tells you, how much of a positive or negative charge it has, and you can addition and subtraction. And then, when you, anyways, so chemists, a lot of what they do is studying how those bindings work, the composition of all the things around us. Okay, pausing to take a breath and also check and see if there are any glaring gaps in what I've explained.
No, I don't. Not yet. I mean, well.
Wait for it.
I guess.
Glaring gap incoming.
Well, so are we talking about the periodic table soon? Because I had a couple things to mention about isotopes.
Let's do it.
And such.
Let's talk about the periodic table of elements. Okay, and okay. Again, I just really want to say that a lot of my information came from Crash Course Chemistry, so you'll hear it better explained there. But anyways, periodic table of the elements, and here I would be remiss not to direct you to Randall Munroe's book, What If? Randall Munroe is the creator of the XKCD, I think I'm saying it right, online comic strip, which is kind of like stick figures, but doing funny stuff. And he's also very well educated. And so he, XKCD, that's right. Does these kind of cerebral and highly educated comics. But anyways, he has this great book called What If? It's the subtitle is Serious Scientific Answers to Absurd Hypothetical Questions, or something like that. And one of them is this. So if you really want to learn about the periodic table of the elements, you should go and check out this book and look at the chapter where he answers the question someone asked, what if you built a periodic table of the elements where you built a wall where each brick was a brick made out of that element.
That element?
Yeah. And it's a real fun read. It's
okay.
So, but anyways, so let's talk about what this periodic table of the elements is. So first of all, as chemists and scientists started to get a grip on how the world is composed, they started to realize that things could be classified. For example, that some elements were lighter than others, and some elements reacted with specific others in certain ways. And to make a very long story short, it determined that we have classified now each element by its atomic number, which is the number of protons in that element. And so if you look at, if you can just Google periodic table of the elements, and if you look at a picture one, you'll see that in the upper left you have the number an item with the number 1, and then in the upper right you have an item with the number 2 in the corner, and then you go back to the left, and it just reads from left to right, top to bottom. The next box is 3, and the next box is 4, then 5, then 6, and they're all in order. We've categorized all of the elements, at least all the elements that we've been able to observe, and in a few cases theorize. Some of these elements are vanishingly rare, but we know they exist in theory because there's got to be some number. In fact, it's kind of a cool story, which I don't really know, but I'll share anyways.
Because that's what we do here.
That is exactly what we do. Before the periodic table of the elements was kind of completed and filled in, scientists, I have to look it up, but there was a scientist who was basically kind of figuring out that there's a pattern here, and was able to predict elements and predict, there's going to be an element that probably has these characteristics and that will have this composition, by following these patterns. So it's pretty cool. And then over time, as we've been able to experiment more and observe more, and we have discovered these these new elements and filled in this periodic table of the elements.
I think you might be no, I don't know for sure, but you might be referencing Russian chemist Dmitry Mendeleev, who is credited with creating the modern periodic table, because he left gaps for elements that weren't discovered yet, but he knew that there was a pattern to how the elements were ordered. So.
Yes, that's right. I was just thinking, Dmitry Mendeleev. Yes, the good old Dmitry.
You and your Russian buddies talk about Dmitry all the time.
Yeah, well, we miss him. He was great at a party. But he was always kind of annoying
120 years ago. So
it's been a while. But
he hasn't.
It was great to have him at a party, but you didn't want him to set up the party, because he would set up the chairs, but he would leave all these gaps. And it's like, Dmitry. And he's like, nope, somebody's going to sit there. And we're like, okay, Dmitry. And sure enough, someone would arrive and they'd sit there. And so, okay. I think we got off a bit. Should we get back on the periodic table of elements? Let's get on it. Yes. Okay, so you have done your homework and you're now looking at a periodic table of the elements. So you'll notice that, the letters in each box, those are the shorthand names of the elements. So that number 1 box, H, is for hydrogen. And then the number 2 box in the upper right, HE, that's for helium, and so forth. Lithium, beryllium, and I'm going to stop now because is number 5 boron? What's the B for?
Because this is learned from a layman, and
baloney.
Layman is not an element, it turns out.
I was just mumbling, sneezing or something. So hydrogen has 1 proton, helium has 2. Fun fact for you, the reason why the sun feels nice and warm when you go outside is because it is busy taking hydrogen atoms and squishing them together into helium atoms. This is called fusion, where you fuse 2 atoms together, and the vast energy released is what powers the heat of the sun, which blasts through the space of our solar system, and in 6 minutes, is it 6 minutes or 8 minutes that it takes light to arrive?
I think it's 8 minutes.
8 minutes.
Yeah, 8.
I haven't timed it with a stopwatch, but someone did.
Well, I did yesterday.
Really? Oh, cool.
Yeah.
It's what'd you do for 8 minutes while you waited?
I read about the periodic table.
Oh, that's
with
cool.
with Dmitry.
With Dmitry. Good. Tell him I say hi. So anyways, the sun is turning hydrogen into helium. Incidentally, that is one of the types of energy that creates a nuclear bomb. There are 2 types of atomic bombs. The ones that were dropped on Nagasaki and Hiroshima in World War II are what we call fission bombs, where they split atoms. They took big, huge atoms with big, huge protons, and then they arranged it so that they could shoot a particle. I think it's a proton, right? Or is it a neutron? I don't know. But they would shoot particle, essentially shooting particles um, into the cores of these protons or these nuclei, and split them up, and then they would those pieces, the shrapnel of that explosion would penetrate other nuclei, and you'd have a chain reaction and kaboom. But they actually discovered a more powerful type of nuclear reaction was when they could arrange for that to happen around a core of a element like hydrogen. So a hydrogen bomb or a fusion bomb, the that huge nuclear explosion would force inward and then cause all those hydrogen atoms to fuse and turn to helium atoms, which would result in an even bigger explosion. So you have now modern nuclear weapons are capable of doing releasing many times the energy of the original nuclear bombs, from the 1940s and 50s. Um, Sorry, little side note there. That's chemistry for you. It's crazy stuff. When I said we're going to talk about crazy chemistry, I was not joking. Um, okay, so in the periodic table of the elements, that number in the upper left-hand corner tells you it's the atomic number, and that's not going to change. Hydrogen is always going to have a 1. Helium is always going to have a 2. Um, Iron is always going to have a 26, and so forth. There are other numbers there that I'm not going to talk about too much, but you get well, maybe I'll let you start on this, Carl, talking about isotopes.
Yeah, well, so an isotope is so like Tim talked about already, inside the nucleus of an atom, you have protons and neutrons, protons being how we're talking about the periodic table, the atomic number. That's fundamentally how you define an element. But the neutrons, well, it turns out there can be varying number of neutrons for an element. So if a atom that has the same number of protons has one more neutron or one less neutron than the first one I observed, those are different isotopes. So those are different types of the same element with just a different atomic mass. And my understanding, so on the periodic table, we have a way of measuring that, and that's just, where does that number show up?
It's like underneath
yeah,
kind of the bottom center, right? At least on the one I'm looking at.
right. Yeah. And that will be more or less double, and sometimes, anyway, more or less double what the atomic number is, because neutrons are usually clustered about, once again, my layman understanding about the rate of the number of protons will be about the number of neutrons you have, but about is the key word, because some have more, some have significantly more, and so you can see that all of those numbers in the bottom, as you're looking at the atomic mass, it's a decimal number. So why isn't it a clean number? There's no part of a neutron. Well, that's because the isotopes exist out in the wild, in nature, and so they average the number of neutrons that we see per element. In the I don't know exactly how they come to these numbers, but it's an average number of neutrons per the frequency of the isotope for that element. And yeah, right, Tim?
And yeah, and exactly. So if you were to gather up all of the explanation that I heard, if you were to gather up all the silver that existed in the world and take the average, count the protons and neutrons, and then take the average, then that's the number that you would get. And it may not always be exactly double the atomic number, because so like in silver, for example, there are I think the most common isotopes have 49 and or no, maybe like 62 neutrons or something. It's like not the number you would expect. It's not exactly 47, but so anyways, it just because of how these atoms are structured, you happen to have some. Um, anyways, it's not random, but un the numbers don't always line up exactly how we would expect, and so you get these average
Right.
numbers.
And
So yeah,
it's possible that an actual chemist or nuclear physicist or whatever would actually be able to expect what the atomic number is based on actual principles of physics and chemistry. But the layman just looks at the number and says, well, that's almost double, or that's well over double for the atomic mass. But yeah, the neutrons in the nucleus of an element is variable, and that's what an isotope is.
yeah. Now, if you look at your periodic table of the elements, you'll see there are certain clusters and categories, and it might be color coded or grouped. You'll see lines and so forth. That's because there are certain patterns that go on. For example, if you look at the far right, you'll see the very rightmost column is a stack of elements. They call them the noble gases, and these have some traits in common. They're all gases, at least under normal conditions, and they are all also very non-reactive. So these are actually useful in, for example, if a chemist wants to create an environment where let's say they're dealing with a highly sensitive or very reactive substance, and so they want to make sure there's nothing that touches it that's going to set it off or cause a chemical reaction or explosion, rapid oxidation or whatever, where oxygen binds to it. Oxygen is one of those elements that is very reactive. They might bathe it in a noble gas, because the noble gases, because of how their atomic structure, they will tend to neither lose nor gain electrons, and so they're not going to react to other stuff around them. There are other metals are another grouping, and metals will tend to have so if you that's kind of in the middle of the atomic or the periodic table of the elements. So you'll see, for example, iron, cobalt, nickel, copper, zinc, and so forth. The metals will all tend to share characteristics too. And this all goes back to what's going on at the atomic level. Because they have this certain number of protons and electrons, this tends to happen. I won't get into it this time, but there are different like rings, I guess, or shells. What is that? Am I using the right terminology,
Orbitals.
Carl? Huh?
Yeah, shells or orbitals. Yeah.
There you go. And a certain amount of electrons can fit in the lowest tiered orbit or shell, and then a certain number of electrons can fit in the next one up. And so if those shells or orbits are filled perfectly, which I believe is the case in the noble gases, then that atom is not going to be too inclined to take on more electrons or lose any, because it's got a pretty balanced state. But let's say you've got just one extra electron floating in that last orbit, that's atom is going to tend to maybe lose that. Or let's say it's just one electron shy of filling an orbit, then that atom is going to really want to fill that, and so it's going to attract certain other um, atoms, and that's why some elements are quite reactive and tend to and I gave
Yeah.
oxygen as one example.
Right. And did you already, so I think you were, I mean, you already talked about oxygen and H2O, but in the case of orbitals, it makes sense as far as the number of electrons. So if you look at your periodic table and see oxygen, you're looking at an atomic number of 8. So that's 8 protons, which means that we'll talk about ions in a minute, but your normal oxygen atom will have 8 electrons, and the first orbital has 2 slots, and then the next one has 8. And so with 8 electrons, you have the first orbital full, first shell, and then you have 6 in the next one. So it would very happily take on 2 extra. And it turns out hydrogen has one little element, one little electron, one proton, one electron just swinging around out there. It's very abundant. And so it loves to bind 2 of these hydrogen atoms with an oxygen to fill that second shell. And that's why we get water, which is pretty awesome.
Yeah, I like water. Water's good.
Who doesn't?
Who doesn't? I've met people. um, and just so these that would be called a reaction, right? A chemical reaction. The two come together and something new is formed. Water is a substance quite different from hydrogen or oxygen. Those two are gases. Water's a liquid. Very different properties. So when chemical reactions happen, the although the atoms themselves are not that, they haven't been changed. It's still oxygen and it's still hydrogen, but the compound changes, and it can change quite drastically. And so sometimes this can happen spontaneously without any extra help. Sometimes chemical reactions can be caused to occur by adding energy. So, and again, oversimplifying here, but a chemist wants to get 2 elements to combine or to react. It may have to add heat, and that heat, provides the energy needed for, say, a certain number of electrons to jump ship, or for the, I suppose jump ship isn't necessarily the right thing, but for them to combine the or to say rise a level in to jump from one shell to another. Is that, sorry, Carl, did I phrase that?
Yeah. And as they jump from level to level, they emit radiation, light. Yeah, so we can talk about that in just. But can I say 1 or 2 more things about the periodic table?
Yes.
Okay, so just generally, I like to understand. So the name, the periodic table, comes from the fact that they're in periods. So the elements are listed in order, atomic number. Tim said that, but elements in the same row are the same period, and so thus periodic. So and that's once again a nod to the fact that there's a particular structure for these as determined by the physics of the atom. But if the periodic table, we have different periods, those are the rows, and then the columns also. So as Tim said, there are different groups of atoms in the periodic table. So the rows are one way to group them, and they have particular characteristics based on their period, on their row, and then they have particular chemical properties because of their column as well. And so column is called group. So there are a lot of ways to understand the periodic table as far as the structure of the table and the orbitals of the electrons, and that's why, like Tim said, why particular groups, particular periods are more likely to interact in particular ways, not only because of the protons, but also the electron orbitals then have a influence on the number of the way that the atoms react, whether or not they're prone to reactions in the wild, or whether or not they need energy or heat or pressure, a lot of it, in order to create a chemical reaction. Once you get that heat, that pressure, and that energy added to the atoms, to the equation, that's when you can break some of these weak bonds of strong force bonds inside the atoms or molecules and create new elements and um, new chemicals, new molecules. And have we talked about molecules? Have you given the definition? And you've talked about molecules. Have we defined the word molecule?
I maybe explained the word molecule, which I would explain as a number of atoms combined together, right?
Right.
There's probably
Yeah, exactly.
all right.
Yeah. Anyway, just okay. So we talked about isotopes. Were you planning on talking about ions?
Let's talk about them. Oh,
Okay.
but also a quick while we're on the table of the elements, just noting that most of the elements that you see in the periodic table of the elements, you won't encounter too much of them in your daily life. The you know in the top 4 or 5 rows, yeah, some of those are quite common, of course, but many of them are quite rare. Many are quite poisonous or radioactive, and especially as you get into the bottom rows, those larger nuclei things start to get a little dicey. And a
Yeah,
lot of
actually,
them
I did.
have only been created in the lab, in like labs or. Right. Oh, sorry, go for it, Carl.
Right. No, and that's right. The last 3 elements, because there are still elements that there were elements added. I think like 6 or 7 years ago, a couple elements were added to the periodic table, and yeah, that's so we know what elements should exist, and so in the lab we can create these high pressure, high energy, high heat scenarios where we can slam 2 nuclei together, and we can get them to, as if I had a role in this, if the chemists or physicists can get the nucleus to stick together, to bond together for, I'm sure, a particular amount of time. I don't know what that is. That then we can say, okay, that's an element.
And that's how chemists and other scientists will flex on each other. They'll, high school athletes, it's like getting the state championship, but chemists, it's like, I made a new element. What you want?
Yeah. You should. I think you get your element that you get to name it after yourself, right? I mean, that's the way it should be.
Or I may put it up for bid.
Right. Let's make some money here. Okay, but
by the way,
before.
It's you buy in now. As soon as Learn It From a Layman gets naming rights to an element, you will be first in line.
Yeah, and we also have beachfront property in Nebraska to sell to you. So
it's very nice.
Very
sweet.
Okay, you mentioned before we move on to ions, the other thing I wanted to talk about was radioactivity, and you already started talking about radioactivity. So in the form, in chemical terms, Tim, do you have, or do you want me to talk about what radioactivity is?
Well, I'll start us off, and then you can kind of polish it off. So radioactivity is when crazy elements do bad things and make your teeth fall out.
Crazy elements do bad things. So I'm taking notes.
Yeah, that's right. Write this down. So certain, some elements are, like I said, very stable. You got your noble gases and whatnot. They're just sitting there. Some elements are very unstable and will actually be shooting out and emitting what's the word? Nucleons. Is nucleons the right word? But like they're shooting out little pieces of atom, and that can cause damage. Okay, that's my less than Learn It From a Layman standard explanation. Now you add clarity and dignity to it.
Well, yeah. So radioactivity, I mean, the basic definition is the release of energy from the decay of the nuclei. And so, just like you said, the larger the nucleus is, the more likely it is to be radioactive. And that, I believe, once again, my layman understanding is purely based on the fact that what bonds together the nucleus, as we said in the beginning, is the strong force. But the strong force is only um, a is really only effective in immediate vicinity. Like you have to be in contact with each other. So with a large nucleus, when you have 80 protons and 100 neutrons, well, it's just the strong force isn't as all encompassing as it is in these smaller nuclei, and so some amount of the of this nucleus wants to split off and shoot off, nucleon, whatever, a neutron, and
And so
energy
what
goes
I'm
with it.
reading here, Carl, says it emits a negative. Too many neutrons in a nucleus lead it to emit a negative beta particle, which changes one of the
Okay.
neutrons into a proton. Too many protons in a nucleus lead it to emit a positron, a positively charged electron, changing a proton into a neutron. And too much energy
Okay.
leads the nucleus to emit a gamma ray, which discards great energy without changing any of the particles. Too much mass leads it to emit an alpha particle, discarding 4 heavy particles, 2 protons, and 2 neutrons. So I guess radioactive
Various.
emissions could be a few different things, but in any case, it's bad for you. Right?
Right. And if you, well, I mean, yes, it is. Don't go and nuke yourself. But the radioactive. So the energy that's emitted is the radioactive stuff, right? That's um, it says the radioactivity is the act of emitting radiation spontaneously. So, and these large molecules, we know that uranium, right, is highly radioactive, and that's why when you're talking about nuclear fission, you have to be very careful because radioactive material, as Marie Curie could tell you, is not something you want to deal with all the time. So, uh, yeah, that's a good layman, I think, basic understanding. Maybe we can have a full podcast on radioactivity, but I guess just basically radioactivity is some amount of decay of the nuclei and the energy emitted from, like you said, in various types of particles or whatever. But that's the this unstable nucleus emitting radiation.
Incidentally, that's happening all sorts in the sun, and so the sun is just beaming out radiation. So the reason we're not all getting like radiated to death is because the Earth has a magnetosphere. The Earth's magnetic charge, it creates actually this giant, it's a giant magnet, and that magnetic it creates this kind of magnetic shield that shields us from the radiation of the sun. This is one of the reasons why we will never terraform Mars, because Mars does not have a strong magnetosphere. And so anything going...
Actually, Tim, I did yesterday.
Yeah. Oh, my word. Well, that changes everything. Shoot. Wait, did you do that before or after you timed the sun?
Yeah, well, Dimitri and I had the nice discussion during that time, and he gave me some ideas.
It all makes sense
now. We have a podcast about terraforming Mars, though, Tim.
Oh, yeah, that's right. That's probably where I okay, huh. Wow, what a good podcast.
Anyway.
We should listen to ourselves more.
Yes, magnetosphere, yes, we should. Well, no, we shouldn't. Nobody should.
But you should, dear listener.
Okay, let's wrap up with a couple more things. So we've got we've talked about molecules. We've talked about radioactivity. Let's talk just briefly about what an ion is, and then we can talk about just some cool chemical reactions that exist out there that we've seen, that the layman has experienced.
All right. So ion, if this is most important when you're playing baseball, as any good coach will tell you, while you're batting, you need to keep your eye on the ball.
Tim.
That was pretty good, don't you think? Oh, okay, if you're not watching, Carl is rubbing his, like, the bridge between his nose, which is a sign that I have just told a very good joke.
Oh my gosh. Okay.
Okay, maybe in the interest of information. So an atom is an electrically neutral, at least in theory, in electrically neutral with an equal amount of protons in the nucleus and electrons orbiting around. An ion is an electrically charged atom particle. So it's got an imbalance. Either it's got more protons than electrons or more electrons than protons. And of course, as you can probably infer from everything we've been talking about here, that imbalance is very significant in how that element will, or that particle will behave, and how it will react to other particles around it.
Right. Yeah. I mean, that sounds a great explanation. Just, I think it's important for the layman to understand ion is not a baseball term. So.
I guess technically not.
Yes. Okay. So ions, yeah, they interact differently with everything. I mean, obviously, as soon as you change the charge of a particle, the way it interacts chemically is going to be different. So, and there are.
Oh, sorry. Go for it.
I was just going to. There are types of atoms that are more likely to become ions because they have, like I said, like one or two electrons in their outer shell, right? What I was reading right before the podcast is that it says ionic compounds usually form when a metal reacts with a non-metal.
Huh.
The metallic atoms lose an electron, becoming cations, and the non-metallic atoms gain an electron, becoming anions.
Which makes sense because cats are a positive influence.
That's not true. Nobody thinks that.
Yes, sir. Okay, raise your hand if you like cats. Okay, good.
You see, there's no hands being raised on the podcast. Nobody on the
That's
podcast.
You
Look,
see their hands.
Go to YouTube. Look right now. There's nobody raising their hand.
Whatever. Go to YouTube and look up cute kitten videos, and then let's see who's not raising your hands.
Okay.
Oh, and,
all right.
Adding to that, the salts are neutral combinations of ions, like sodium, a positive ion, and chloride with a negative ion. So.
Okay. Let's finish up the podcast with a couple. Oh, I did have the anecdotes I wanted to share about my chemistry teacher experiences. So, Tim, while I'm sharing these, you can come up with your examples of chemical reactions in the wild that the layman is interested in. If you can come up with something interesting. It's first for everything. First time for everything. Okay. Okay. So chemistry teachers matter. Even so, now you've been with us almost an hour and listening to Tim. Tim is generally a good teacher. Now, whether or not he's a good chemistry teacher is
highly questionable.
Well, it's not really questionable anymore, is it?
Yeah, that's right.
Essentially questionable an hour ago, and now the answer is known. Anyway, my dad, who was generally an English professor, near the beginning of his career, for all of you English majors out there, turns out getting an English teaching position at a university is probably approximately like winning the lottery. So my dad was teaching, he was a chemistry teacher at a high school because his minor was in chemistry, because what English major's minor is not chemistry.
But your dad could have taught pretty much anything.
Come to think of it, actually, it may have been a major. He may have double majored, and one of them may have been.
Right. I think
chemistry.
he, was majoring in it, and then he switched at the last minute and got a doctorate in English.
In English, that's correct. Yeah. Anyway, so he was obviously very good. We had chemistry sets when I was a kid, all that kind of, so there are good chemistry teachers out there. And then I was taking AP biology back this is obviously high school, and we had a great AP biology teacher, but he got in a very serious motorcycle accident and almost died, and was out of commission for multiple months. And for those of you that have taken AP courses and or are currently taking AP courses, you can't go without a teacher, without a qualified teacher in an AP course for long. And that's where so they brought over a sub that generally subbed for chemistry, and he started trying to teach biology, AP biology, and it was a train wreck. It was, I mean, it was 8th grade biology. Anyway, and then they brought over the AP chemistry teacher to teach AP biology because they knew that we needed whatever help we could get. And he was very, very good and very qualified, because it turns out biology has a lot of chemistry in it. So the quality of your understanding of chemistry often has to do with the quality of the teacher. So we apologize.
That's right. Don't judge chemistry on our account.
Okay, let's talk about a couple of reactions and then we'll wrap up here. Tim.
Okay, my reaction is going to be fire. So when you light something on fire, it is undergoing a chemical reaction. And in short, it's the whatever is being burned is reacting with the oxygen in the air, and the heat is causing it to stuff is combining, and then so a lot of what is created is dissipates into the air. We see it as smoke, and then the ashes are the substance that remains. But that's a chemical reaction. So you start with one thing, say a piece of wood, and you end with another thing, a pile of ashes and a cloud of smoke composed of lots of different stuff. But the key component in that reaction is the oxygen. Without oxygen to fuel that reaction, to continue that reaction, the fire stops. And that's why if you throw a wet blanket on a fire, it will soon stop burning, because it's you've deprived it of oxygen, which it needs to make the chemical reaction happen. So there you go. Fire.
Fire. Very nice. Okay, I've got two. So one is the one that we experience all the time, literally, and at this moment you are doing it, and that is O2 to CO2, and that is respiration, right? So you breathe in, and among the various things coming into your body when you're breathing in is O2, and that's oxygen. That's the stuff that our body needs. And that's the oxygen molecule that we then take in, and it interacts inside our body with glucose. And glucose is apparently C6H12O6, which I didn't know, and you won't remember either after this podcast is over. But the chemical reaction between our oxygen molecule and our glucose produces CO2, or carbon. Adds a carbon to that molecule, and that's what we breathe out. And so that chemical reaction happens all the time, and it's what keeps us alive.
I'll see
So
your Oh, sorry.
No, go ahead.
I was going to say, I'll see your respiration and raise you a photosynthesis.
Ooh.
This is kind of the opposite. This when plants take in carbon dioxide, and using energy from sunlight and water, they produce energy, or they produce their cellular energy and release oxygen. And so this is part of, I suppose these two could be put together in a oxygen cycle, right? The oxygen, we breathe it in and incorporate it and breathe out the carbon dioxide, and then plants take in the carbon dioxide and use it and incorporate it and put out the oxygen. And so it's, the circle of life. Incidentally, before the rise of respiration, well, the first creatures to to breathe in oxygen and produce carbon dioxide apparently caused a mass die-off, billions of years ago on the Earth, because they changed the composition of the atmosphere over time. It's kind of interesting to think about. But now we've got a nice balance, I guess, as long as we don't like throw it off by, taking all the carbon and dumping it back into the atmosphere. So yes, that might be problematic.
Who would do that, Tim? Who would do that?
No, nobody. Well, I did today, actually. Sorry.
Yes. Okay. I was going to wrap up with one last one, unless you have another one, Tim.
Go for it.
Oh, all right. So this one's chlorinated water, right? So this is your swimming pool. To some degree, your drinking water, though hopefully to a smaller extent. And this is chlorine is a chemical that we pour into our swimming pools or dump into our swimming pools and our drinking water to a small extent to kill bacteria and viruses. And chlorine, so it says chlorine solution you pour into water breaks down into many different chemicals, including hypochlorous acid and hypochlorite ion. Both kill microorganisms and bacteria by attacking the lipids in the cell walls and destroying the enzymes and structures inside the cell. And they do this, it's an oxidation thing, and as they get oxidized, the bacteria and enzymes die. So that's how the chlorine gets in. So it creates this hypochlorous acid, which is a neutral, and the bacteria is trying to fight away charged particles. And so because this is a neutral particle, it gets inside the cell, but it still has the chemical structure to go and attack these proteins that hold the bacteria together and then neutralizes them. So thank you, chlorine. Good job.
Luckily, you're not a monocellular organism, so it doesn't have as negative an impact on you. Wait.
Yes, it does. It does have an impact on my skin and hair, and generally it does. It interacts with your skin to some extent. Well, I mean, there's a reason you don't drink super chlorinated stuff, because it will do the similar effects on your own biology, but we're more resistant, and we have various layers of epidermis, so we're generally okay.
Yeah, don't drink.
Anyway, okay.
Don't drink pool water. Biggest takeaway.
Don't drink pool water.
There's other reasons you shouldn't drink pool water too. That are.
We'll have a different podcast. We already did, where we talked about Johnny talked about body functions. So.
Touche.
Dr. Johnny, yes. Okay, well, thank you, Tim. Good job. I now feel like I know something.
I feel like I understand more what I don't know about chemistry.
Yes, unlearn it from a layman. So,
that's right.
Okay, well, let's check out real quick with our listeners are. So we're doing well. Once again, I've mentioned Northern Canada really doesn't tune in much, but the Northern Territories did tune in this last month to our insurance podcast. Yeah, so apparently they need to be insured against icicles.
That makes sense. It's a dangerous place up there.
Glaciers. Who knows? I mean, what can attack you? An elk? A rogue moose?
Bears.
Bears. There we go. Yep. Let's bring it all the way back around. So.
That's right.
Anyway, we thank everyone for listening. Hopefully this is helpful, and we'll be back again soon. Thanks.